Hello everyone and welcome to the MATLAB and Simulink Robotics Arena. In today's video, we'll be talking about programming soccer robot behavior. In this video, we'll see how to create what we call a system-level simulation of a simple robot soccer game. So these little robots that you see moving around here, they're all acting on their own based on some kind of information about the environment around them. For example, sensing the locations of the ball, other robots, or their position within the field. And throughout this video, you'll see in detail how we implemented this using MATLAB and Simulink. The soccer field system can roughly be divided into these three parts. You have the soccer field, which represents the physical system that we're trying to control in some way. So these are the robot dynamics, the ball dynamics, how they move around the field, and so on. Then you have the individual robot behavior, which is going to be a big focus of our video. So this is, again, given all the sensor information or the state of the environment, how does each robot behave? And then finally, if this is how your system is architected, you might also have some kind of centralized behavior. You can think of this as the referee that, for example, it might be looking at the ball and determining whether there was a goal or the ball is out of bounds and possession has changed. And this then controls how every other player in the environment will react. What we'll show is with MATLAB and Simulink that we're going to create a system model or a model of this entire set of components that represent the complete robot soccer game. And we'll end this by also showing how this is useful for actually implementing things on your real robotic soccer system. So for example, the centralized behavior or that referee might go to a controller PC. This is something that's typically set up in these robot soccer tournaments where you have a PC that's measuring the locations of the robots, the ball, and then setting the state of the game. And also, of course, taking the individual robot behavior and putting it on each board or each computer that the robot is running. Now, before I jump to the software, I just want to show you one more quick thing, and that has to do with the main feature of how we're going to develop this robot logic and behavior. So think of something like this. Let's assume that our robot attacking logic just consists of three different states or modes. If you don't have the ball, you need to search for it and then go to it. Once you happen to hold the ball as an attacker, you want to then take it to the goal. And if you're close enough to the goal where you think it's appropriate to shoot or attempt to shoot a goal, then you're going to kick it. And if you end up scoring a goal, then that's great. The game continues. Or if the ball is still in play, then you want to go back to that initial state of searching for the ball and trying again. So we're going to show how this can be implemented using a tool called Stateflow, which looks like this. If you architect everything correctly, then you really can make the stateflow charts look like your back of the napkin diagram of the behavior of the system. And the thing about stateflow is, first of all, that it integrates with MATLAB and Simulink, but also they contain some very specific modeling constructs that are useful for autonomous behavior, such as this robot soccer game. In particular, the ability to model finite state machines where you can transition between modes, and depending on which mode you're currently in, so there's this memory component, the same information might lead you to make two different decisions. And that can be a little tricky to do with traditional text-based programming. This typically involves somewhat complex chains of, for example, if-else statements or switch case, and so on. So let's see how this looks in Simulink. Simulink is going to be the main canvas here for our system integration. As you can see, I've got three subsystems at the top level that represent the same three squares that we showed in the system architecture initially. We have the soccer field, the individual robot behavior, and that centralized game controller. And each of those has its own implementation. So again, the soccer field really represents the simulation or the part that is physical that you're eventually going to replace with the real world. This uses some combination of MATLAB and Simulink to create these simple dynamics of the robots that you see on the field. And I won't dig very much into that except for one portion, and that is with the ball simulation, where we actually are still using stateflow to model what we call a hybrid dynamic system. What I mean by a hybrid system is one where you can switch between some kind of dynamic system of equations and something that might just be purely algebraic. For example, here when the ball is held, the position of the ball in this simulation is just going to be attached to the position of the robot that's holding it. So there really isn't any dynamics because those are already dictated by the robot itself. On the other hand, if you transition over to the ball-free state, this actually is what we call a Simulink state. And this becomes a dynamic system. It's a first-order damped system in the velocity. So what you're really saying is when you kick the ball or when the ball comes loose, you're going to assign it an initial velocity. That velocity is slowly going to decrease because of that damping coefficient that we've put in the dynamic system. Now, the interesting part is really in the individual robot behavior. So I do want to focus a bit more on that. I'm basically just replicating the same behavior logic for all of the robots on the field. And each of them is then represented by this state flow chart. Again, that it receives the sensors, the behavior, and outputs the commands that are going to be sent to the robot. You're going to start seeing some fairly complex chart behavior. First of all, let's focus on the things on the left. As you see here, you've got a little bit of a flow chart here, which says that every time you're executing behavior, you're going to check the commanded role that you're given to the robot. Is it an attacker? Is it a defender? Or is it a goalkeeper? And if so, you're going to go into one of these other state machines for that specific mode. For example, let's go back to that attacker mode that we talked about before. Here you see the three states that we identified in the presentation, which were go to ball, go to goal, and kick ball. And the things that you want to note, each state has some text that tells you what's happening at different points. For example, when you enter the state or while you remain in that state, then there's MATLAB code that executes. And these are actions that are specific to you being in this mode. The other important thing is dictating the transitions between modes. So for example, let's focus in on this transition here between the go to goal and the kick ball action. This transition here is guarded by what we call a condition. So this is saying you're only going to switch between these states if, first of all, you're in the original state, the go to goal, and if the following expression evaluates to true. So all of these things, again, can be programmed in this environment and tested in simulation. So one thing that I'll show here is it's just one benefit of Stateflow is that while you run the simulation, you can actually use the Stateflow editor to keep track of which state you're currently in. As the simulation is running, you see that the active state of the system is going to be highlighted in blue. And you can also, mouse over and take a look at specific data that's occurring, what the values of things are. You can put breakpoints if you want to debug between these transitions. So it's a pretty good prototyping tool that then can become the actual code that you put on the robot. Now, there's one other thing that I've sort of left out, which is that to make this code somewhat readable, there are quite a few features that we're using here. And I want to run you through a couple of the key ones. First of all, you see everything here that's highlighted in this blue or teal color is what's identified as a function in Stateflow. Instead of writing out these big blocks of code, you can certainly, just as you would with any other code, create functions that can abstract some of that behavior. For example, let's take this track detection function. If I go up to the top level of the chart, you see that I've defined a collection of these functions, and one of them is this track detection. So if I go in here, this is what's known as a flowchart, where I'm accepting some inputs and outputs and then going through some logic that's reminiscent of an if-else statement, right, where I'm doing this calculation graphically. Now, in my case, I did this function graphically, but you could also make this be Simulink blocks or MATLAB code if you really wanted to. So there are ways to basically wrap any of these modeling languages, MATLAB, Simulink, or Stateflow, into functions that you can then call in your higher level supervisory logic. The other things have to do with this text that you see in the transitions, that at a first glance, you see that things are kind of structured to be easy to read. For example, in this transition that I've highlighted, I'm checking some kind of condition on whether the role of the robot behavior is equal to the attacker role, right? And there's a lot of MATLAB going on in here to make this happen. So two things. One is the idea of structuring your data so that your diagram looks clean, and that's where the behavior.role comes from. If I go up one more level, again, you'll notice that this chart has two inputs, sensors and behavior. But these two inputs are what are known as Simulink buses, or you can think of them as structures in Simulink. These are data types that you can define that contain some collection of heterogeneous data. So for example, what I'm really saying is that all the sensor information is now squashed into one signal. Same with the robot behavior that you're setting, and same with the commands. And we can check this by going to the bus editor in Simulink. So I'll open the bus editor from the dialog, and you'll see this window coming up where I have 4 different bus data types that I've defined that represents the game state, the robot behavior, the robot commands, and the robot sensors. Let's, for example, dig into the robot sensors, right? That this bus contains 4 elements. The object detections, the pose of the robot, a Boolean flag on whether the ball is held, and the detections of the other robots. And I can dig into any of these and click them, and you see on the right side, it tells me what data type these are, what their dimensions are, and so on. So this is really a good way to structure your data, and it has implications for that generated code as well. I just want to quickly show you then the robot behavior, because this has an interesting one. The one that I want to highlight is this role, which you see its data type is set to an enumerated data type. Enumerations are a good way to add readability to numbers, essentially. Okay, if I go to MATLAB, you see that I've defined a couple of these enumerations as MATLAB files on the left here, and role is one of those enumerations. Here you see that I've defined a role enumeration that's subclass from an integer enumeration type. And what this really does is just maps numbers to readable text that helps the model be self-documenting. Basically, the numbers 1, 2, 3, and 4 map to the 4 different roles that the robot can take in this soccer game, right? Attacker, defender, goalkeeper, and none. So with all of that, I think we're ready to take a look at that generated code. I will go over to the pre-generated code here by opening that code generation report. And again, you'll now see that on the left side, I have a couple of files, and the ones that are most important here are the C or the source file and the H or the header file for the soccer behavior. So you see I can either scroll through the code and look at what's going on, or I can click through the chart in this web view and hone in on where this particular behavior corresponds to the code. Again, the nice thing here is because we've used all these structured data types and enumerations, then the generated code also maps to all of that, right? So for instance, in this code that I've highlighted, all the structures like commands .robot velocity, they take that same structure as the bus we specified. And you can also see that actually if you go to the types file here, this header file, all the data types that we defined, whether they be the buses or the enumerations, are included here in these type definitions. For example, my robot sensor bus data type in C now becomes a struct that contains the following fields. And similarly, our enumerations, so this role enumeration that we defined now has these type defs for attacker, defender, goalkeeper, and none. And all of this can then be used in that code. So to recap, we use Simulink to create the system model of the entire soccer game, including the physical system and the individual robot behavior and the centralized behavior. We then use Stateflow to convert some kind of concept of how we think the robot should behave to something that's actually executable, debuggable, and can generate standalone C code. And finally, we're able to manage our models for readability, for controlling the generated code using these structured data types called buses. And furthermore, we're able to represent certain discrete modes with enumerations. And that takes us to our key takeaways for this demonstration. We perform system-level modeling with MATLAB and Simulink. Stateflow lets us decide state machines. We showed a lot of different techniques to manage the complexity of your model. And that code generation then lets you go out to standalone code. Or even if you want to target hardware, there might be some of our hardware support packages where you can directly take this code and build it on any boards that we support. So as always, thank you for watching. I hope you try out this model. And if anything, you know how to contact us and how to find more information. Thank you.